Today in physics, we're going to begin a new unit on rotational motion. To start off, we're going to begin talking about center of mass. We've kind of been talking about mass and objects and forces acting on them all year long, but we want to address this a little bit differently as we move into this rotational unit. To talk about an object's center of mass, we would say that this is a point on any object where we assume all of the mass acts at that one point. This could be a place where there is mass or a place where there isn't mass. But the Earth will apply a force on that one point. So some objects are very symmetrical, some objects are not so symmetrical, some objects can change their center of mass like you and I, and some objects can't. They're a fixed center of mass. But mathematically you can kind of think of center of mass as sort of a weighted average. Where is all of the mass? Where on the object or near the object is all of the mass technically located? A lot of times we can think about finding that center of mass by simply trying to balance something. If I take an object that's really symmetrical, like a meter stick, and I simply support it, and I don't even have to really look at my hands, but if I just kind of slowly bring my hands together, they'll settle in about the center of mass of this object. And so this object is supported at 49-ish centimeters. Now you'd think, well, it's a meter stick. It's 100 centimeters long. Why is it at the 50? Well, remember that this is not a very crystalline material. It's made of wood. It's kind of pulpy and irregular and not super uniform in its density. So the center of mass can also be thought of as that balance point. Now you could also balance things that don't have a uniform position, like this knife, for example. It seems to balance closer toward the handle end than in the dead center of the object. If you were to cut that object in half at that point, the question would be, is there more mass on the left side or on the right side? Maybe that's not so intuitive, but if we took another object, like this broom, for example, this broom has definitely one end heavier than another. If I try to grab it in the very center of the broom, it wants to topple over. But it turns out that even something like this, you can use the same strategy and just slowly bring your hands together, not really paying attention, and they'll move and settle in at the center of mass of the broom. So the center of mass of this broom is much closer to the bristle end. If we were to cut this right here and place this end on a scale and place this end on a scale, the question is, would they have the same mass? The answer, of course, is no. This end is much heavier than this end. But it's about where, like a weighted average, where is that average position located? So to find the center of mass of something, it's helpful to have a coordinate system, a place where we can measure from. How far away from zero is that center of mass? So consider this seesaw, and it's put at a position where it could rotate. There's a pivot point, so to speak, and then you have a 70 kilogram mass placed at the left side and a 30 kilogram mass placed at the right side. Well, the center of mass of a seesaw, just the board itself, is going to fall in the center of the board, very much like the center of mass of a meter stick. So we could see that the center of mass of the seesaw would be more like here. But how about the center of mass of this whole system? We have a lot more mass on the left than we do on the right. And so the center of this system will shift to the left. And if we consider that balance point, it turns out that it would balance here at this pivot point. Sometimes we call that a fulcrum, a pivot point. And if we measured, well, how far away is this 70 kilogram mass from that pivot point? And how far away is this 30 kilogram mass from that pivot point? We would find, so the 70 kilogram mass is 1.3 meters away. The 30 kilogram mass is 2.7 meters away. The difference in masses is, 30 kilograms is more than, twice as small. And so it's going to be more than twice as far away from this origin. And that's kind of how we deal with an average or a weighted mass. Now, many objects are solid or uniform shape. Think of a basketball or any kind of ball, really. Objects that have a uniform shape are going to have a center of mass in their geometric center. And sometimes there's mass there, and sometimes there's not. For example, with a basketball, certainly it might be full of air. Or think about a donut. A donut has a center of mass where there is no mass. Or a bicycle, or a chair, or a teacup that's empty. All objects have a position where Earth's gravitational field is going to pull on that one point. And that's actually true of even you and I. If you take geometrical objects and you stack them together and you want to find the center of mass of this system, then that combination of objects, you would find the center, like for the circle and the stick. I find the center of the circle, I find the center of the stick. I'm going to draw a line between those two centers, and the center of mass of this system should be somewhere along that line. We also have center of mass in 3 dimensions because we're all 3-dimensional. So you have a center of mass in an X dimension, a center of mass in a Y dimension, and a center of mass in a Z dimension. This would be like into the board or out of the board. So what happens if you support something at the center of mass? Well, it balances. But what happens if you apply a force away from the center of mass? Well, that object will begin to rotate. Here I have a couple of tennis balls suspended from a string. In this case, they happen to be even. If I give this a toss, the center of mass of this system is about here, and so it should rotate at about that point. And so if I toss it, you can see kind of that it spins around its center of mass. However, if I take this other tennis ball pair and I toss it, this ball is filled with a very heavy material, whereas this one is empty. And so the center of mass is much closer to the heavy end. And so if I give it a toss, you can see it doesn't rotate the same way. It rotates about its center, which is very close to the heavy ball. So if you take a hammer and you flipped it through the air, you would see that it would rotate about that pivot point as well. So we can balance things, we can observe things through the air, and actually it turns out that we can use a mathematical relationship to also find the center of mass. This is where a coordinate system is even more important. Remember that if we're looking for a position to say this is the position where the center of mass is, in physics we use position as x or y. And so our equation for finding the center of mass is that we would look at each individual object and its mass and figure out how far away it is from some origin, and we would put these things together. So we have an equation for finding the center of mass that says the x center of mass, CM stands for center of mass, x is position. So the x position of the center of mass is equal to, now this says sigma xi mi. So remember, sigma stands for the sum of, and then I would stand for individual things. So it's the individual x position and the individual mass. We would add up all of those things together, and then we would divide this by big M. Big M is the total mass of our system. So we can find this horizontally. If we had something on a coordinate plane, we would measure from an origin. Hey, how far away is this piece, or how much mass is at that position? And then we could do this vertically in a y dimension, and obviously you can do it in a third dimension from a z-axis. And this will give us the x or y or a z center of mass. There are similar equations that exist for velocity and acceleration. We really won't spend too much time in there. I just want you to understand how we could find the center of mass and what happens when you apply a force there versus applying a force away from the center of mass. So let's take a look at an example here. Here we have a sample problem where we have a coordinate plane, and you can see that we have an x-axis and a y-axis. These intersect here, and we have 3 points. We have a 2 kilogram place, a 3 kilogram place, and a 1 kilogram place. And it asks us to determine the center of mass of this system. So let's just look at the X position of the center of mass, because from an X perspective, these are not all located in the same place. So how would you do that? We would say that the X center of mass is the sum of the individual distances times the individual masses divided by the total mass. So let's take the 2 kilogram mass, for example, and we want to find what its X position is and its mass first. So our X center of mass is going to be the X position of this 2 kilogram dot is at -1. So it would be -1 times the mass, 2 kilograms. And then we want to do that for each of the other points. So if we look at the 1 kilogram dot plus the X position of that 1 kilogram dot is a 0 because it's lying on the y-axis. So it's going to be 0 meters times 1 kilogram. This was -1 meters times 2 kilograms. And then if we look at the third dot, the 3 kilogram block or circle is located at an X position or an X coordinate of 2. So it's going to be, say these are meters, 2 meters times 3 kilograms. So we've got each individual mass and its location from an X perspective. Now we want to divide this by the total mass. So this is going to be 1 kilogram plus 2 kilograms plus 3 kilograms. So if we factor through this out, we have -1 times 2. The X center of mass is going to be -2 plus 0 plus 6 divided by 1 plus 2 plus 3 is 6. And these were all kilogram meters, the units up at the top. So then we come to the X center of mass is going to be -2 plus 6 is 4. So this is going to be 4 kilograms times meters over 6 kilograms. Now these units will go away. And the X position is at 2/3 of a meter. Well, where would that be on the grid? Well, if our origin is simply here, and this would represent 1, then 2/3 would be about here, somewhere in there. Here we go. We could do this the same way for the Y position. We just now look at the Y values of each one. The 2 kilogram would be located at a Y value of +2. So we would repeat this same process, but looking at the Y position for the center of mass. We'll change this to a Y. The Y center of mass would be the 2 kilogram we said is located at a +2, so it's going to be 2 meters times 2 kilograms plus the 1 kilogram mark is located at a -2 for the y-axis. So -2 meters times 1 kilogram plus, and then our 3 kilogram is located at a -1 meters. So -1 meters times 3 kilograms, all divided by the total mass, 2 kilograms plus 1 kilogram plus 3 kilograms. And so if you math through this, then we've got 4 plus -2 plus -3, and this would all be kilogram meters, over 6, 2 plus 1 plus 3 is 6 kilograms. So 4 minus 2 is 2, minus 3 is -1, so we would have our Y center of mass is -1/6 meters. -1/6 meters, so this would be just barely below the origin on the y-axis. And that's how we mathematically find the center of mass. But the key is, I have to have an origin. I have to have some place to measure from. Center of mass causes some interesting changes for us when we are just living our daily lives. There are things that we have to do differently because we would prefer not to fall down. For example, our center of mass is located about at your belly button. A little different for all of us, some a little higher, some a little lower, but about belly button height. And your center of mass is kind of in your body and it's over your feet. And as long as your center stays over its support, you don't rotate. Rotating for people is bad when we don't want to. We also call that falling. So if you were to try to do this little activity where you touch your toes, you know, you simply bend over and touch your toes. But if we made you do this where you had to put your heels against a wall, try this at home. Put your heels against a wall and your butt against the wall, and then take your hands on your quads and just slowly run your hands down your legs until you get to your toes. Try to see if you can touch your toes from that position without falling over, without toppling. You'll find that it becomes quite difficult. We've done some other activities where we try to take advantage of center of mass, whether we try to lift a chair with our head on the wall, or talk about changes in your center of mass. Man, over a period of about 9 months, a woman's center of mass changes significantly. And you'll frequently hear people talk about as the baby gets bigger and bigger, though, you'll hear frequently talk about, oh, my feet hurt really badly, or I feel like I'm clumsy and I'm tripping all the time. Why would you be doing that? You and I have figured out where our center of mass is, and we're kind of navigating that world pretty easily. But if your center of mass changes over a fairly rapid period of time, your body has to relearn, oh, hey, I need to kind of do things a little differently because my center of mass is changing. For a woman who's pregnant, certainly your center of mass is going to get a little lower, and it's going to keep moving forward and forward and forward. Once that gets past your toes, that, you know, you have to do stuff to keep yourself from falling over. That would be awful if mom fell over. So you've probably seen the pregnant woman walk, right? They get the belly out here and they lean back and they hand on the hip because I got back pain. Why do I have back pain? Because I've had to lean back to counteract this belly out here. And so you see the pregnant woman walking like this, trying to maintain that balance, but it becomes quite painful and quite challenging. So there's a couple of different video links that I would encourage you to take a look at as you make your way through this section of notes that deal with examples of center of mass. And we'll continue to experiment with this topic. Our concern will be more like, how do we get something into equilibrium, and what happens when an object's when you apply a force away from the center of mass, and looking at those things. So if you have shapes that are complicated, or you have points that, you know, we had a grid where we had spread out different positions, when we find the center of mass, we will use this equation. The x position of the center of mass is the sum of xi times mi. So individual distance times individual mass, add those all up, and we divide by big M, total mass. Anything else is going to be a lot more complicated, and we won't talk about that in AP Physics 1. We're only going to kind of take this as far as we need to so that we can talk about torque and those types of things. But remember that we've talked about Newton's second law, how a net force causes a mass to accelerate, and when we deal with the center of mass of a system, when you apply a net force at the center of mass, it will cause that entire system to accelerate. And so if you have a problem that involves a system of a lot of particles, we can make this a lot simpler. You know, if you talk about how is the solar system accelerating through around the galaxy. Well, we could treat the entire solar system as one point, a system of particles all treated as a single point. That one point would be the center of mass of our solar system. With everything moving, our center of mass constantly changes. There's a center of mass system between the Earth and the Moon, and that position constantly changes because sometimes the Moon is closer and sometimes the Moon is further away, and it pulls on the Earth, and we stretch, and we see the effects of these forces all the time, especially when it comes to talking about our tides, high tides and low tides. So if we look at a system and we say all the forces on the system are internal, we have a very large system, then the center of mass is not going to change. Let's say that you're standing in a canoe, and the system is you and the canoe, and want to reach forward and get your bananas out of the cooler. So you kind of work your way forward to the canoe. If the canoe's in the water, the canoe and you are one system, the center of mass of that system is not going to change. Well, if you move one way, the canoe has to move in the opposite direction to counter and keep that center still in the center so that the whole canoe doesn't dump over. An external force that acts on all of the particles can be simplified by considering that it acts on the center of mass. And then we change Newton's second law to say net force equals mass times acceleration of the center of mass. So lastly, I want to take a look at one problem. This is a canoe problem. So here you have a canoe that's represented by this brown rectangle, and we have the center of mass of the canoe located by this black dot in the center of the picture. Then we have two people sitting at opposite ends of the canoe. We have Romeo and we have Juliet. And clearly Romeo and Juliet don't have the same mass. And we can tell that this is Juliet because she has long blonde hair. So we're given the mass of each person, and we have the canoe. The black dot represents the center of Romeo, the black dot represents the center of Juliet, the black dot represents the center of the canoe. So very similar to how we had that grid that had 3 different particles in 2 different dimensions. Now we've broken this down a little simpler to just considering an X dimension. Here Romeo sits at the back of the canoe, 2.7 meters away from Juliet, a 55 kilogram woman who sits at the front. The canoe has a mass of 80 kilograms. Find the center of mass of the system. So we would do the same thing, but we need to know where are we going to measure from. It's very frequently helpful to run your origin right through the middle of an object. If I do that, and I'm dealing with individual distances and individual masses, if I run my origin right through the middle of the canoe and I say, how far away is the canoe from the origin? It turns out it's 0 meters. And so that makes my math a little simpler. I could have put it through Romeo or through Juliet. It doesn't matter, but you have to keep that origin the same. And certainly if I'm measuring a distance to her or a distance to him, and this is my origin, Juliet would be at a positive distance away, Romeo would be at a negative distance away, and then you could kind of follow the math along and find the center of mass of the system. I really encourage you to take a look at the boy on the paddleboard problem. It's pretty cool because they have a young man standing on a paddleboard and he'll move, and then you can see how the paddleboard moves in relationship to him. All right, this takes a lot of practice, so make sure that you're paying attention to it and kind of draw it out, sketch it out, and we'll continue to use center of mass as we move into our unit on rotational motion.